Like most Silicon Valley startups, we started with a big idea in a small garage. This is the founding team of Planet Labs in our garage in Cupertino, California, the same town in Silicon Valley where Steve Jobs and Steve Wozniak built the first Apple computer. We had come from mostly NASA backgrounds, working on small satellite technologies. And when the co-founders, Robbie, Chris, and Will, decided to leave NASA, they asked me to come with them. So I did, because of that idea. The big idea was to use space to help life on Earth, to launch a fleet of Earth imaging satellites to image the entire Earth every day and democratize the access to that information. When we think of Earth imaging satellites, we typically think of something like this. It weighs 2.5 tons, took 5 years to design and build, is designed to last in orbit for 10 years, and cost $1 billion end to end. That's billion with a B. Remote sensing satellites are typically big and expensive, which means that you can't launch very many of them. And the number of satellites that you have in orbit is directly proportional to how often you can update the imagery. Here's the same satellite for scale. With these types of satellites, the average age of a satellite image that a typical consumer has access to is about 1 to 3 years. On a global scale, 1 to 3 years is the age of an image that we're working with today. When we think of satellites, we think of this. Meet the Dove satellite. We call our satellites Dove because they're peace-bringing satellites. In the traditional aerospace world, you often think about satellites as birds, but they're given very predatorial names, like hawk or eagle. Our satellites are on a different type of mission. We're focusing on commercial, humanitarian, and environmental applications because we want to take better care of our planet. We treat our satellites like software, what we call agile aerospace. Release early, release often. Or in the satellite world, launch early, launch often. And when we say a product launch, we actually mean it. Over the last 18 months, we've built 12 full iterations of the Dove satellite, 12 major upgrades to the design over the last 18 months, compared to the traditional approach, which takes 5 years to build one. So what's the difference? Well, in the traditional model, failure is not an option. You're making a satellite that's big and expensive, so it has to work. And for it to be able to work, you have to use components that have already been proven in space. So you're taking components that are already old. They're proven, they know how to work, but they're old. So when you're flying your satellite mission, it has technology that's 10, 15 years old. The latest NASA Mars rover that was launched in 2011 carried a 2-megapixel camera. 2 megapixels in 2011, and our smartphones can do better than that. For us, failure is expected on some level. We're launching large numbers of satellites across large numbers of launches so that no one satellite can take down the fleet. Our satellites are so small that they can launch on pretty much any rocket. And often we go in the extra capacity not taken up by the bigger guys, what's called piggybacking or hitchhiking. And we've even launched as cargo to the International Space Station. So I'll show you a video of what that looks like. So that long structure is the space station's solar array, and that white box is where you want to look. That's our satellites being deployed into orbit. We'll see a closer look in a second. Pretty cool. To date, we've launched 71 satellites. This is kind of crazy, but that's more satellites than most nations on this planet. And that's from a small startup in San Francisco. Yeah. Currently, we have 24 of those satellites operating in orbit. Some of them more satellites are still waiting for deployment from the space station, but a lot of them have already deorbited. And we launch the satellites to low altitudes so that once their lifetime has expired, they fall out of the sky, burn up in the atmosphere, and don't really contribute to the orbital debris. So we're not leaving our junk around. But we are designing these satellites for short lifetimes so that we can continuously upgrade the technology. So we're never launching with 2-megapixel cameras. To get to the full constellation, the full fleet, to image the entire Earth every day, we need 150 satellites. And when 150 satellites are operating in one orbit, they act as a line scanner, sweeping the Earth as it slowly rotates underneath the satellites. And each satellite has a very simple mission. Our idea was always to keep things as simple as possible. Take pictures about once a second, and then downlink the information when over a ground station. This was the first image that we ever captured from our first satellite, launched back in April of 2013, Dove-1. And we actually had no idea if the satellite would even work. So this was a pretty big surprise to us. Looking at the image, we could see that we could count trees, see different plots of land. There's a lot of information that's captured from such a small satellite. So we got the validation about some of the applications we were dreaming of. So for instance, if you think about deforestation, if you were monitoring deforestation and you had a snapshot once a year, you could see where trees were being lost. But if you were monitoring deforestation and you had a snapshot once a day, you could see where trees were being lost and then go investigate the cause. I'll show you some more of the images that we're capturing. We're downloading thousands of images a day right now. This is a solar power plant in rural China, one of the biggest ones in the world, seeing China invest in clean tech. This is a farm in Arizona, and you can see some different irrigation techniques. So those circular patterns are what's called pivot irrigation, one of the most efficient ways to farm with limited water resources. And this is maritime traffic in Egypt on the way to the Suez Canal. So these pictures are beautiful, but they're static. We're used to a static picture of the planet. The real value comes when we can start to see the change. So on the left, you'll see the publicly available image, and on the right, the one that we took. This is another town in rural China. And the difference between the two pictures is about 1 year. So we can see roads are being expanded, a new bridge was constructed. There's a lot of investment going on in the infrastructure. And this is the type of change that you can see on a time scale of about a year. Over here, again, publicly available image on the left, our image on the right, and the time difference now is 1 month. So this was taken in Nevada, and those dark spots are evidence of flooding. So we looked at the weather reports from the previous month, and we saw that there was heavy rains. So you can see the areas that are being affected by the flooding. You can imagine some insurance applications of this, or if you saw flooding on a daily timescale, you could better protect your assets. And finally, this is an image we took in Brazil. On the left, publicly available image. On the right, our image. And this time, the timescale is 1 day. So we took 1 day newer image. And the change here is pretty obvious to detect. In this scenario, it looks to be a controlled fire. But what if it wasn't? Wouldn't you want to know right away? Our planet is incredibly interconnected, and change is happening at an incredibly rapid pace. If we want to be able to take better care of it, we need to know what's going on, because we can't fix what we can't see. We also have an artist in residence program at Planet Labs. We have an artist come in to get inspired by what the engineers are doing, And then the engineers get inspired by what the artist is doing. And he really got excited about one of our applications, potential applications, to track migratory animals. So he came up with his design. And we liked it so much, we put it on our satellite. So this is what the satellite looks like with the solar panels deployed. It's our little art exhibit in space. So we're no longer in the garage, and there's 80 of us instead of 8. But our mission is still the same. Image the entire Earth every day and get the data to the people who need it. Get it in as many hands as possible. And the things that are really excited about, the applications that we're really excited about, are the ones we can't even think of, because we want you to think of them. So now that you know that this imagery is coming, what are you going to do with it? Thank you. I think we have some time for questions.
Tell you what we think. We've got some questions here, and we'll just freestyle it. First question here is, how sure are you the information can't be misused for non-peaceful purposes?
Sure. So like any tool, you can't really control how it's going to be used. But our strategy is to make sure that the initial partners that we give the imagery to are using it for overwhelmingly good purposes. So we're partnering with commercial entities and nonprofits so that the conversation starts out on the right foot. And I don't think we can guarantee that there will be no bad coming from this imagery, but we hope that the overwhelming implementation will be for good.
Thank you. I mean, what about Antares? That happened a couple days ago.
That's right. So that's actually some unfortunate news. We had 26 satellites on the Antares rocket that was launched on Tuesday, and then actually that rocket failed. So our satellites blew up with that rocket. And really, as I mentioned in the talk, we launch early and we launch often. So we spread the risk across numbers of different launches and numbers of different satellites. So while it's unfortunate, we'll keep going because we already have replacement launches booked, and it's something that we've already expected from the beginning.
So you expected something like that might happen? So
that's right. We don't hope for it, but we plan for it.
Makes sense.
Yeah.
Good question. What's the price for launching a satellite? How much is it?
Sure. So the market price for launching one satellite of our size is about $300,000. And then you get some bulk discounts for launching in large numbers.
So it's a big Lambo and you can shoot it up into the sky.
Right.
That's nice. Next question is, how do you prevent your satellites from hitting other satellites or the IS?
Yeah, the ISS, yeah. So the nice thing about our satellites, even though they don't carry propulsion, when they fold out their solar arrays, they can maneuver using what's called differential drag. So when the wings are out, you can either fly edge on or face on, and the drag force, based on the different orientation, can move your satellite around. So if there was a potential collision, we can move our satellite out of the way with about 24 hours notice.
24 hours notice?
Or less, it depends.
Is that fast in rocket terms?
It's enough time to predict a collision and then do something about it.
OK, fair enough.
Yeah.
What are the smallest structures you can see on the images?
Right, so the resolution is about 3 to 5 meters per pixel. So we can see trees, we can see buildings, but we can't really see individual people.
OK. The next question is, what about live imaging video like Skybox offers, who was recently bought by Google?
Right. So we don't do live video. Our focus is on getting a full snapshot of the entire Earth every day. And so we leave things like video to other people, which I think is really cool, but it's not in our model.
Here's a great question. Where can I apply to work for you?
Our website is planet.com, so check it out.
Do you take people that yell?
What's that?
Do you take people that yell and say, I want to work? Who wants to work for him?
Yeah, if you yell
Look
loud
at that.
enough, OK, great.
Good. How does the satellite manage to point the camera to Earth?
So on board, we do have ways to control the way it's pointing. There's 2 systems. One is a magnetorquer, which is a coil of wire where you run a current through it, which creates a magnetic field that you can push off of the Earth's magnetic field. And then we also have little wheels that we can spin up and spin down. So there's systems on the satellite that can point where it's going.
I don't get that question, but it seems to be popular. Do you have live feed of war zones?
So we image the entire Earth. That means that we're getting everything. So we're not really focusing on any one specific area, but we're capturing everything that's going on. So.
Okay. And then, for people curious, is how many satellites will you need to map the entire Earth every day?
Right. So we need 150 satellites operating at the same time to map the entire Earth.
Here's an interesting question. How do you earn money, and will your data be public?
Yeah. So right now we're partnering with commercial and nonprofit entities so that we're having these one-to-one contracts. Eventually, we'd like to open up the data to everybody. And we're thinking about things like a freemium model or priority access to higher paying customers. But that part of it is still under development.
Okay. And can you give some examples of how your partners use your satellites? Use cases.
Sure. So deforestation monitoring is one. Wildfire monitoring. Even for mapping, that if you could see that bridge there's a road construction there, that could be really useful information to update your maps so you're giving people correct navigation.
And here's a good question. Where do you see yourself and your program in 5 years? And what do you dream of at night?
Sure. So we're not at the 150 satellite constellation yet, so it'll take us some time to get there. But to be able, I think that one of the biggest advantages we can offer is the continuity of the data. So not only are you getting daily refresh, you have the whole history of everything that's behind it. So you can see the trends and you can see continuity. And so I think that providing that stable set of imagery is a really good place to be in 5 years.
There's a certain Sergey, I have no idea how it could be, who's just disappeared but said, will you be selling it to Google and how much?
No comment.
Okay, fair enough. Next question is, sorry Sergey, whoever you are, I have no idea. How did you get planet.com? We went to the internet and
we
bought
asked
it.
very nicely. We're saving the planet. How could they not give it to us?
That's how it works, is it?
Yeah.
So, hello, I'm saving the planet. Can I
That's
have
right.
planet? Oh.
Yeah.
Good to know. Can you install some laser on satellite and then shoot people with it? That could have been me. It's awesome. Can you do that?
No comment.
No comment. Awesome. That's so cool. How are you different? And it's not cool shoot, but like in a 13-year-old thinks it's awesome. How are you different from Google Earth Engine?
Sure. That's one of the platforms that could potentially take our data as a feed. But I think that Google is working on their own stuff right now, and there's a lot of people who might be interested in applications that are not specifically tied to Google, and them getting your information and how you're using it. So
okay.
It could either work together or it can work separately.
And here's quite an interesting question, which just disappeared. Can I launch my own satellite with you?
Come find me after. Yeah.
That sounds like romantic, doesn't it? Can we launch a satellite together? How much data do you collect each day?
I don't know off the top of my head. We're downloading thousands of pictures a day, and that's only going to grow because we still have a ways to go in terms of the numbers of satellites in orbit.
And here's a question that I was expecting that to come. Who manages space regulations?
Yeah. So there's a number of different bodies. The UN manages radio spectrum allocations, and then there's US government agencies like the FCC and Department of Commerce that we have to get permission from to be able to launch these satellites. That's one of the things that I personally do, is go and get these permissions.
Awesome.
Yeah.
It's been an absolute pleasure. Thank you so much, Mike Pioneers. Make some
much.
noise if you liked it. Right that way. We'll be back in a second. Don't go away.